So now we're going to look at complete or strong induction on natural numbers, and this is also meant to be a review. So as you may know, strong induction is also used to prove properties of the natural numbers. So again, we'll let p of n be some property of the natural number n. And again, our goal is to prove that p of n holds for all n and n, or to prove that p of n is true for arbitrary n. So now, in some cases, we need to use what's called strong induction to prove this property. So in some instances, we may be able to use simple induction, but in some cases, we may need to use strong induction. Now, strong induction is very similar to simple induction. So what are the similarities? So the first is that it has, again, two cases. First, we consider the basis case, which is exactly the same as for simple induction, which is to prove that p of 0 holds, or that the property holds for the first natural number 0. Then we also have the inductive step, which involves an induction hypothesis. But here, in strong induction, our induction hypothesis is a bit stronger than the induction hypothesis for simple induction. So we assume the induction hypothesis that the property holds for every natural number k strictly less than n. So instead of in simple induction, where we simply need to assume that the property holds for the natural number n minus 1 or the number strictly preceding n, in this case, in strong induction, we need to assume that the property holds for every natural number less than n. So from 0 all the way up to and including n minus 1. And then, just like as in simple induction, we need to prove that the property holds for the natural number n. So this is a quick review of the form of strong induction. Again, let's consider an example to see how to apply strong induction. So again, we're going to come back to our robot case. So suppose that we need to prove that the robot R can go up the staircase to any arbitrary step, just like in our example before. However, now our robot looks a little bit different. It has 3 legs, and in order to climb the stairs, each leg has to be on a different stair. And so we are going to need to use a proof by strong induction, so we need the stronger induction hypothesis on the step number in order to prove that our robot can get to any arbitrary step n. So just like before, our basis case is the same. So we need to prove that our robot R can get to the beginning of the staircase, step 0. Now our induction hypothesis is that if we can assume that R can get to any steps k less than n, the induction step tells us if it can get to any of these steps k less than n, it tells us how to get to n. So the reason we need this stronger induction hypothesis is because in order for our robot to reach step n, we not only need to have that we can go from n minus 1 to n, but we also need, in the induction hypothesis, how to get from n minus 3 to n minus 2, and from n minus 2 to n minus 1. So since we need to know how to do a lot more, we need a stronger induction hypothesis in this case. Okay, so that's an example of how to apply strong induction and when it's needed, when we need a little bit more of an assumption to tell us how to get to step n, for example. Again, notice that in fact strong induction really isn't any stronger than simple induction. What I mean by this is, let's consider why strong induction actually is a valid form of proof. Why is it that it actually can tell us how to get this robot from 0 up to step n? Well, with our basis step, it tells us how to get to 0. And then with the induction step, if we know how to get to 0, the induction step tells us how to get from 0 to 1. So that tells us how to put this one step from 0 up to 1. Then, if we have one step on 1 and one step on 0, we can apply the induction step again to tell us how to move from, well, we know how to move from 0 to 1, so that gives us our second leg from 0 to 1, and our first leg to get from 1 to 2. And then in the third step, right, our last leg is on 0, so we know how to get from 0 to 1, and we know now how to get from 1 to 2, and the induction step applied again tells us how to get from 2 to 3. If we continue to apply this induction step, it tells us how to get from 0 up to n in a number of different steps. For further explanation about this, please see the notes on Moodle. Okay, so in the next video, we're finally going to be able to look at a framework for proof by induction of well-formed formula.